So today we're going to use some of the properties we've seen previously as a way to solve equations. These will be both exponential equations and logarithmic equations. And we have two main methods. Now here it says there are three basic strategies, but two of them are practically the same idea. So this is one method that we will use. This works if you are starting off in exponential form. It might look something like this. The idea is to make the bases the same. Rewrite the given equation in the form that uses these one-to-one properties. This is an example of a one-to-one property. So if the bases are the same, then that means the exponent on the left has to equal the exponent on the right. You see them listed here in the box. That's the one-to-one property we're talking about. Now, it can also be in logarithmic form, right? So if you have a single log on the left and a single log on the right of that equal sign, so you only have one term on the left, one term on the right, if the bases are the same, then that means the value of which you're taking the logarithm must be equal on both sides as well. So that's a one-to-one property. So that's the first thing we try to do. If that doesn't work, then we have these. And these are really the same concept. We're going to rewrite it. So if we're starting off with an exponential equation, we're going to convert it into a logarithm. And if we're starting off with a logarithm, then we'll convert it into an exponential. So those are really the two main approaches. We try this one first, and that doesn't work, then we can rewrite it. So there it is, a review of those one-to-one properties. And these are also properties that we will use from time to time, sort of in this section here. Remember, this is an exponential form. There's your base, there's your exponent, but inside the exponent is a logarithm. Remember, if the bases are the same, then it's as if they cancel themselves out. They do, because they're opposite operations. They're inverses of each other. And this guy right here is what you are left with. That's your answer. This is the other way around. Here we're starting off with a logarithm, and we're taking the value of an exponent, right? So there's your base to the power. So again, if the bases are the same, they undo each other. They are inverse operations, and that's your answer. So we're going to start off with a few problems where we're simplifying. We don't have equations yet, but then we'll get to the equations below that. And that's mostly what we're doing today. Also, we will be using the change of base formula. So let's put that down here in case you don't remember. So let's say you have log base x of y. What you're going to do is create a fraction. This is log of y over log of x. So notice what's happening here is the base is not a base anymore. It sinks to the bottom and becomes the value of which you are taking the logarithm in the denominator. So that means this is our common base of 10. So you just use your calculator and just punch that in. Okay, so we're starting off with a few simplification problems. Notice that these are not equations because there is no equal sign, as opposed to a problem like number 4 where you do see an equal sign. That's an equation. So because we do not have an equation in number 1, we're not actually solving for x. We're just simplifying. So here I have the natural log. We understand it has a base of e, and that matches this base, and this base has an exponent, right? So that means the logarithm and the exponent cancel each other out. So you're just left with the 2x minus 1. Same idea in number 2. Here's the base of e, and in its exponent is a logarithm. So the exponent and the logarithm are inverse operations. They cancel themselves out. And so you're just left with x squared plus 2. Here in number 3, we have this constant term of negative 4 in front, so it's just going to sit there for a while. Look at the second term. There's your base of e, raised to the power of natural log. The bases match. They cancel out. They undo each other. And you're left with the x to the 4th. And that's as far as we can simplify it. So those don't take very much work at all. Let's talk about our equations now. All right. Starting off with problem number 4, we have 2 to the power of x equals 32. We're going to look at using method number 1, which is, can we make the bases the same? We usually take the bigger number, the 32, and try to rewrite it as 2 to some exponent, right? What kind of an exponent do I need? I guess I don't need those parentheses there. I got carried away. So 2 to what power is 32? And again, you might not know off the top of your head. You can use your calculator to guess and check, saying, hey, is it 2 to the power of 4? Is that what I want? No, that's just a 16. Is it 2 to the power of 5? Yeah, that's it actually. So let's replace the 32 with a 2 to the power of 5. So this is the one-to-one property. If the bases are the same, then the exponent on the left equals the exponent on the right. And there, we've solved for x. Now, before we go on to number 5, let's set up an alternate example 4. So call this 4 part B. Let's use this example of 2 to the power of x equals something else, like 40. Now, you can see the structure is the same. They're exponential. In the first problem, we could rewrite the 32 in exponential form, 2 to the power of 5. But in this alternate example, I cannot match the bases, right? I cannot take 2 to some power and turn it into a 40. It doesn't work. So if that first method fails, then what we have to do is go to the alternate approach, which means to rewrite the exponential as a logarithm. Okay, so let's rewrite this as a logarithm. 2 to the power of x equals 40 means it will be log base of 2 of 40 equals x. And look at that. We've isolated the variable just by converting formats. If you like, you could put x here. And now, how do we find the value of log base 2 of 40? This is our change of base formula. Log of 40 divided by log of 2. Right? So you'll go right to your calculator, you'll type that in, and always use 3 decimal places in this section here because these values are very sensitive to small changes, meaning like logarithms and exponents are very sensitive to small changes, to small inputs. So we want to make sure that we have a bit more accuracy. So these kind of represent the 2 methods that we're going to be using. Either you can match the bases or you can't, and if you can't, then you change the form. So the rest of these problems are all just variations on that. Here's number 5. Log base 4 of x minus log base 4 of 8 equals 0. Hey, if you have a 0, then that means there's nothing there. Let's send one of those terms to the other side. So you have log base 4 of x equals log base 4 of 8. Hey, check that out. This is our one-to-one property. We saw that up here in our box. If the logarithm on the left equals the logarithm on the right, and they have the same base, then that means these values must be equal. So that means this x must equal this 8. So there you go, x equals 8. We see a similar problem here in number 6. Here we have 2 logarithms on the left-hand side. We have the 0 on the right. Let's add natural log of 3 to both sides. So natural log of x equals natural log of 3. Notice we have one term on the left, one term on the right. They have the same bases, so x equals 3. All right, let's look at more examples on the next page. All right, number 7. Here we are. So 1/3 raised to the power of x has to equal 9. So we're going to start off by trying to make the bases the same. And part of what I'm thinking is hey, 3 and 9 have something in common. 9 could be replaced as a 3 squared. And so we'll do that in a moment. First, we don't want fractions. Take that denominator, move it across the division bar. Remember, when you do that, you always change the sign on the exponent. So that means you have an exponent of a -1 and the exponent of x that they gave you. There's the 9. Now you want to try and make the bases the same. So 3 to the power of -1x equals, change that 9 to a 3 squared. Now this is our one-to-one property. If the bases are equivalent, then those exponents must be equivalent as well. Isolate the variable by dividing away the negative sign. So -2 is your answer. All right, so again, we could take this exponential form and make the bases the same. So contrast that with number 8. This is also exponential. E to the x equals 7. But here I cannot make the bases the same. I cannot just rewrite the 7 as some e to the power of who knows what to get me a 7. I don't even know what that would be. Right? So I cannot make the bases the same. So what do? We change the form. Turn this into a logarithm. With the base of e, that means we want the natural logarithm. Natural log of 7 equals x. So when you convert the form, look at that. It isolates the variable for us. And that's it. So notice this is the exact answer. And some of the book problems will leave their answer key like this. But if you type that into your calculator, we'll get a decimal value. We're approximating it to 3 decimal places. So 1.946 is what it tells us. And this is your approximate answer, right? So interestingly enough, some of the book problems have its answer key like this. And honestly, I have not been able to figure out a rhyme or reason as to why the book sometimes leaves it as an exact answer and sometimes as a numeric answer like this with an approximate answer. So we'll just use the decimal. That's fine. Here's number 9. Natural log of x equals -3. All right. I don't have logs on both sides. I can't match the bases. So we have to convert the form. Remember, this is your base of e, and there's your exponent of -3. So e to the power of -3 equals x. There's the exponential form. Notice x is already isolated. There's my exact answer. If we throw that at the calculator, we will get a decimal value of approximately 0.050. All right, next row of examples. Here's number 10. Log base 3 of x equals 4. Again, I don't have logs on both sides to make the bases the same, so we have to convert. There's the base. There's the exponent, equal sign x. Right, so 3 to the power of 4 equals x. Hey, the variable is isolated. So that means x is 81. Here's number 11. Again, we have this fraction here. So first step is let's lose the fraction, move the 64 into the numerator. So 4 to the power of x minus 5 on the left, that will equal 64. Now it has a negative exponent, and that is in turn being raised to the power of x plus 2. So now we have exponents on both sides, and we're trying to match the form. Can we take that 64 and replace it with 4 to some exponent? So the left looks the same. The right-hand side, we want to take the 64 out, and that means we still have the exponent of -1, we still have the exponent of x plus 2, they're all being multiplied together. So let's take the 64 and replace that with 4 to some power. So 4 squared is 16, we want 4 cubed, that's 64. So now this is our one-to-one property. If the bases are the same, then the exponent on the left must equal the exponent on the right. And again, those are all being multiplied together. So what we will do is we'll take this as a -3 and we'll distribute it to the binomial. So we have a -3x and a -6. So let's solve this linear equation now. Moving my terms of x to the left-hand side, I'm adding 3x to both sides. Now I'm adding 5 to both sides and dividing away the 4. So our final answer for x is -1/4. Number 12. Again, we have an exponential form. There's my base of 5 to the power of x plus 2. I can't make the bases match because they don't have any other factors. So we need to convert it to logarithmic form. So we need a log with base 5. So log base 5 of 3 equals the x plus 2. So you'll notice that our x isn't quite isolated. We'll have to subtract 2 at some point to get x by itself. But at least it's on our main line of text. It is not stuck up here in the exponent. So how do we know what log base 5 of 3 is? And that's when we bring in our change of base. Going to my calculator and typing that in, 0.683. And then subtracting 2 from both sides to get x by itself, so -1.317. So up to this point, all of our examples have fallen into these basic categories. We make the bases the same, or we have to change the form. All right, that's what we've seen a bunch of. So these last 2 problems at the bottom of the page, we still have to do that, but they have a little extra step that we have not seen previously, so there's a little extra going on here. So take a look at number 13. Now, if you compare number 13 with some problems that we've seen previously, and we'll take you back to the page, to the previous page. Notice we have 2 logarithms on the left-hand side, and here it's set equal to a value of 2. So if you compare that with what we've seen in problems 5 and 6, notice here we also have 2 logarithms on the same side, but that was set equal to a 0. So we were able to restructure this so you had a single term on each side, a single logarithm on each side. The point is you have to have 1 term with a logarithm and 1 term with a logarithm. When we're looking now at number 13, if I were to move 1 logarithm to the other side, it wouldn't be by itself. We'd have this extra term of 2. So yeah, we would have one logarithm on each side, but it's not the format we need. We need a single term on the left and a single term on the right, but we don't have that. We would have 2 terms on the right side. So we can't just move the logarithm over. We need something else. Instead, let's condense, right? We have learned how to both expand and condense, and condensing is a nice trick because that way we turn this into just one term, right? So with the addition sign, that means we're going to be multiplying these factors. So x times 5, I just put the 5 in front. So that's a neat trick. Now we only have one logarithm. So I can't make the bases the same because I have only one log on one side, so let's turn it into exponential form. This is the base of e. So e to the power of 2 equals 5x. And if you divide by 5, that's your exact answer, but let's turn that into a decimal. So my calculator tells me e squared is 7.389, and then I'll divide that by 5. So my final answer is 1.478. Notice that we've spent a few turns approximating here, right? So e squared is an approximate answer, and then we divide that approximate answer by 5. We're approximating again. So we tend to lose accuracy the further on we go. That's one reason why we are keeping 3 decimal places, because it will still be slightly more accurate than just working with 2. Here's our last one. This is our exponential form. I have a base of e. I have a base of 91. Again, I cannot make the bases the same. So we need to turn it into a logarithm. But I can't do that just yet. Because if I'm going to turn this into a logarithm, like maybe some of these that we've done previously, compare that with number 12. Here we turned this into a logarithm right away. That's because this base was by itself. I mean, there were no other numbers that you were adding or multiplying. It was just a base and its exponent. That's good. That's what we want. Here, number 14, my base of e to the power of 3x is not by itself. We have this multiplier of 4. So your first step is to isolate the base. So that's what we're doing here. Isolate the base. Now, the exponent is part of the base. That's what I'm talking about. We want the e to the 3x to be by itself, so we're dividing both sides by 4. So e to the power of 3x equals 22.75. Now I cannot make those bases the same, so let's turn this into a logarithmic form with the base of e. So natural log 22.75 equals 3x. So again, as I go to the calculator, I'm going to be approximating this value of 3.125, and then we're dividing that by 3, so we're approximating again. So we do tend to lose some accuracy when we have these multiple steps, but that's good enough. We have the approximate answer there.